All right, now we are starting in Unit 3, which is Chapter 5 and 6. So I'm going to go over Chapter 5 in this lesson. Chapter 5 is just about basic probability. So if you've had any classes that have covered some probability in them before, just a basic math class, you've probably seen some of these concepts already. And so this chapter shouldn't be too bad for you. Chapter 6 is going to be the one that probably is going to introduce some newer topics to you when we get into the binomial. But chapter 5 is really just going to be a lot about terminology, just understanding what probability is in general. So you can see 5.1 says it's about probability rules. And so in probability rules, we're talking about some of the laws and some of the terms that we'll be using with this probability. So if we look here at this experiment 1 and 2, what I did here was we're flipping a coin and recording the proportion of heads, all right? So you'd see what we're looking at on this graph is the first flip we got tails, so that means 0 out of 1 would have been heads, right? So we didn't get any heads, we flipped it one time, so we've got 0 out of 1. The second flip we got heads, so now we flipped 2 times, so our denominator would be 2, and one of those has been heads, so we would have 1 over 2, which would give us 0.5. So that's where all these points are coming to, all right, are coming from. So we've got experiment 1 where we did that, experiment 2 where we did that. Both of these we did 100 times, okay, 100 flips. So this says after 10 flips, what is the proportion of heads for experiment 1 and 2? So if we look at experiment 1, it looks like 10 flips is somewhere in here. So we've got the proportion of heads is about 0.7 or 70% of our flips were heads. Over here in experiment 2, on the 10th experiment or the 10th flip were around 50% on that one. After about 100 flips, what is the proportion of heads? Here you see we're approaching that 0.5 number, and also the same thing over here in experiment 2. So after just a few trials, we see that our two experiments had different answers, right? This coin was giving us about 70% heads. This coin was giving us about 50%. So does that mean that this coin that we used here was biased in any way, or maybe that the person flipping this coin did not do it correctly? Why did we get 70%? Because we should expect that heads and tails, if we have an unbiased coin, we should get 50-50, right? So why in this first experiment, after only 10 flips, did we see 70% being heads when we expected to see 50%? Well, the answer is that in just a few trials, we are going to see unpredictable proportions, okay? So the proportion that we expect to happen, that 50% that we expect to have heads, is not always going to happen in the short term, okay? Probability is something that we expect to happen in the long term. So after many, many experiments, we expect, or many, many trials, we expect to see this proportion happen. But it may or may not happen in the short term. Okay, so the law of large numbers says that as the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. So what that means is I expected to get 50% heads, right? After I did this 100 times, I saw that on both experiments, I was getting close to that 50% mark. However, if I just looked at one flip or two flips or three flips, I may not see that probability happen. So probability is something that's going to happen in the long term, all right? So just because it doesn't happen in the short term, just because that one experiment didn't see that happen after 10 flips doesn't mean anything was wrong with the experiment or anything was wrong with the actual coin that we used. It just means that we didn't do enough trials. Okay, let's go on to the next slide. So some terms we're going to be using with probability. An experiment is just a repeatable action where the outcome cannot be predicted with certainty. So choosing a sample, rolling a die, flipping a coin, all those things we don't know what the outcome is going to be beforehand. An event, which we represent with E, is a specified result that may or may not occur when an experiment is performed. So choosing a female out of a group of students, okay? So maybe you want to see what is the probability that I will choose a female when I'm choosing a group for a sample, okay? Or what's the chance I will roll a die and get a 5? Or flip a coin and get tails. Okay, so that's the event we're interested in. The sample space, which we represent with a capital S, is the collection of all possible outcomes of an experiment. So you would write down all the possible outcomes. So for example here, if we're trying to define the sample space, let's define the sample space for choosing students from a college class and recording their gender. So our sample space, our capital S is equal to, we usually use this set notation here, and we could put male comma female, or we could put M and F. Sometimes we'll use just capital letters just to abbreviate, just to help save space, in writing when we're putting things down like that. Number two, rolling a die and recording the number rolled. What are the possible outcomes we could have there? So we have 1, 2, 3, 4, 5, and 6. Those are all the possible outcomes. So that's our sample space. The same thing with flipping a coin. So the rules of probability. The probability of any event has to be between 0 and 1 inclusive, okay? So it can't be less than 0, can't be more than 1. Because we're thinking of probabilities usually as decimals. We're thinking of them as proportions, or you could think of them as percentages if you wanted to, and then they would be between 0 and 100%. But as proportions, as the decimal, they're going to be between 0 and 1. Then the sum of the probabilities of all the outcomes, or everything that we listed in that sample space, has to be equal to 1. Okay, so when we calculate or figure out what that sample space is going to be here, when we calculate the probability for each of those events, okay, and add them all together, it's going to equal to 1. And the reason why it would equal to 1 is because that says that that is sure to happen if the probability is equal to 1. So one of those events has to be the outcome, okay? So that shows that we have listed all the possible outcomes. Okay, for a probability model, that just lists all the possible outcomes and each outcome's probability. It has to satisfy the rule of probability, which means that all of them together add up to equal 1, and all of the probabilities are between 0 and 1 inclusive. The impossible event means it could never happen, so the probability of that event would be equal to 0. A certain event means it would always happen, and the probability of that event would be equal to 1. So looking at that, just trying to get a visual idea of what we're talking about there. Down here, if we're looking at the probability of red, okay, so I'm going to choose one of the marbles out of the bag and see what's the probability that I would choose a red marble. Okay, so that's our probability of red here that I'm notating. The big P is doing probability. You see, you could write it this way with probability of red. You could just write probability of R, and understand that that meant red, okay? So here, I am certain to choose red, right? The probability of red here is 1 because when I choose a red ball or choose a red marble out of there, there's 6 red marbles and I'm going to choose 1. So I have a 6 out of 6 chance of getting a red marble, right? When I'm over here, now I've added 1 blue marble into the mix. So now what's my chance of choosing a red? Well, now I have a 5 out of 6 chance of choosing a red, right? So now I'm still pretty likely to choose a red, but it's not certain. It's possible that I could choose a blue, right? Here we're equally likely. Here now I'm getting unlikely to choose a red, right? It's more likely that I would choose a blue marble. And here it's impossible to choose red, okay? So this is a fairly easy example. I know you all probably look at this and say, yes, I get that. Here it's certain, here it's impossible. But what I want you to start thinking about is how to think of probabilities. The closer a probability is to 1, the more certain it is to happen. The closer it is to 0, the more impossible it is to happen. Okay, and we're going to be dealing with probabilities throughout the rest of the semester. So it's a very important concept understanding what probability is telling you. Okay, it's telling you the likelihood that something would happen. So an unusual event is usually something that we would say has a low probability of occurring. So what would be considered low? sometimes it's 5%, sometimes it's 10%, but just something that's very unlikely to happen. If I tell you you have a 30% chance of winning some lottery, you would think, that's not too bad odds. That's pretty good chance. But if I say you have a 0.3% chance of winning the lottery, well, then you're going to say, well, I don't have a very good chance of winning, right? So you want to think about, is this a likely event or is this going to be an unusual event? Here's when we're calculating some probabilities there. We've got two ways to calculate probabilities, the empirical method and the classical method. Okay, the empirical method we're going to use when we actually have data and we've collected that data and we're going to calculate some probabilities based off of it. Classical method is you don't actually do an experiment, okay? You're just going to rely on counting techniques. Now, not everything can be done with the classical method. It has to have equally likely outcomes. And so, like rolling a die or flipping a coin, all those we could do the classical method with. But many things we're just going to have to do the empirical method with because there's not a way to do the classical method. Then we've got the subjective method, which basically we just kind of touch on here just to let you know that there are going to be some probabilities that are given, especially in the media and the news, that you're going to see that really aren't calculated using the empirical or the classical method. So it's kind of a catch-all for anything else goes into that subjective method. Okay, so talking about the empirical method here. The empirical method, we're going to look at the relative frequency of E. Remember you did relative frequency charts back in, I guess that was in chapter 2. You did relative frequency charts. So our relative frequency is just the frequency of E over the number of trials of an experiment. So that's what we actually would have done in this experiment. We would have used empirical probability there to figure out what's the probability I would choose someone that's Protestant or Hindu. So we're using this collected data, this relative frequency, to then create these probabilities. The empirical method is going to produce approximate probabilities, right? Since every experiment is going to be slightly different, like when I went out and I didn't do this, but whoever went out and got this landscape survey there in 2014, probably everybody wasn't included, right? So if I went out and did another sample, these percentages might change slightly, right? So since those would change a little, we're going to say that the empirical method is giving us approximate probabilities. But as we increase the number of trials of a probability experiment, so as I get more and more people included into my survey, those results are going to be closer and closer to those true probabilities that come from the classical method. So what that tells us is if we can get enough people into our sample, then the probabilities that we base off of that is going to be pretty close to what the true probabilities are. And that's really what we use in inferential statistics, right? We're using those statistics to infer about the parameters. So the larger our sample sizes, the closer our statistics are going to get to being equal to the true parameters. Okay, so on this example, again, we're looking at a frequency chart there. And so we're looking at a national survey conducted by the Center for Disease Control to determine college students' health risk behaviors. They were asked, how often do you wear your seatbelt when driving a car? Now, this is not one we could necessarily do the classical method on, right? Because we don't just off the top of our head know what percentage of people will sometimes wear a seatbelt, right? The only way we're going to know that is to go out and collect data, to ask people, or to do an experiment or whatever. Somehow we're going to get data back on this. As opposed to when I'm flipping a coin, I know that I have a 50-50 chance of getting heads or tails, right? There I already know there's some classical probability I can do. With this, I can't, so I have to do empirical probabilities. So when I do these empirical probabilities, I'm just calculating the relative frequency, okay? So I'm taking my frequency, dividing by my total sample size. So up here, my probability here would be 0.026, or my relative frequency is 0.026, same thing, right? This is a probability model, and so when you're trying to answer that question, what you need to show is that this adds to 1. So adding up all the possible outcomes adds to 1. What is the probability that a randomly selected college student wears their seatbelt sometimes? So you'd go here and say, well, 345 divided by 4521 is 0.076, and that's it. Is it unusual for a college student to never wear a seatbelt? Well, we go up to never. We see that our relative frequency is 0.026. So only 2.6% of the time would you find a college student that never wears their seatbelt. So I would say that's unusual. It's unlikely that that would happen, which is a good thing. Okay, classical method here. Classical method, I said, we'd use with rolling a coin, flipping a coin, rolling a die. So these are things where we know what the expected outcome is going to be. Okay, so the classic example in statistics for probability is where we have a bowl with lots of different colored marbles, and you're going to choose different colored marbles out. What's the probability? Now we look here, we're going to have 22 total marbles, okay, based on this, what it told us here. What's the probability I would get red? Well, there are 6 red over 22 total. I do 6 over 22, I get 0.273. Now I didn't actually go and do this experiment multiple times and then record my results, right? So this isn't empirical probability. This is classical probability. This is what should happen. And if I do with empirical probability, if I try to do it that way, if I do enough trials, so if I try this many, many times, I should start to get empirical results that look very similar to what these classical results are, okay? Okay, subjective probability. So subjective probability, like I said, is kind of the catch-all for, well, what if I don't use empirical or classical probabilities? So for example, this was around this time last year. It said the Broncos own sixth best odds of winning Super Bowl 50. So they had about 14 to 1 odds, so about a 6.67% probability. Now, how did they do that? I mean, did they use empirical probability? Did they use classical probability? Well, they can't really use either of those, right? We can't use empirical probability because empirical probability means that we're going to actually go out and do an experiment or collect data. So how would we do that with a Super Bowl? Are we going to make them do some trial runs at the Super Bowl? I mean, we can't really do that, right? So we can't do empirical. Classical probability, there's definitely no way we can do that because there's no way we just automatically would know um, what the chance is that any given team would win the Super Bowl. So this instead is based on probably some other mathematical models, but not any classical or empirical probabilities. Okay, so this is kind of based on the writer's knowledge of what who's on the team this year, who their coaches are, who they're going to be playing, what the other teams are doing, all that kind of stuff. Okay, over here, this is a Facebook page that I follow a lot. If you're in Western Kentucky, you probably know about Bo Dodson. If you don't, you should probably follow him on Facebook. But he has a really good forecast when it comes to, especially in the winter months, when it comes to snowfall and all that kind of stuff. He's always right on um, about if we're going to get snow, if we're not, and all that. So I always follow him because I'm originally from Paducah. So we always, followed him when I was there. And so now I still follow him even though I'm over here in Bowling Green. But anyway, that's beside the point. But he will kind of put some of this information out where he gives the probability of so much snow falling. Okay, so you can see these probabilities he has here. Now, is he able to do empirical or classical probability? Not really. He really is just basing this on his knowledge of, okay, we've got these temperatures happening, we've got this wind direction, we've got this amount of precip in the air, all this stuff happening, and then that helps him to know um, what he thinks the chance is that we're going to get snow or we're not. Okay, so this is all going to be subjective probability based on his knowledge of things that have happened in the past. Okay. All right, so moving on to some rules that we'll use with probability. We have the addition rule, and then we'll get into the multiplication rule. The addition rule, we have to define events first. Two events are disjoint if they have no outcomes in common. They can also be called mutually exclusive. Okay, so you might see some examples where they use Venn diagrams here. So Venn diagrams are going to represent our sample spaces. So here we've got event A and event B. Here event A and event B cross. So what we could be talking about here is, let's say, event A. So our experiment we're doing first is from a deck of cards, choose one card. Event A is choosing a heart. Event B is choosing a spade. Now you notice they have no outcomes in common, right? They don't cross any because either I choose a heart or I choose a spade or I choose something else and I'm in this other area, right? Here, event A and B, A is choosing a face card, B is choosing a spade. Now, I could choose a face card, or I could choose a spade, or I could choose a spade that is a face card, right? And so those would be their common outcomes. If they have common outcomes, then they are not mutually exclusive, right? Because then they can occur at the same time. If they don't have any common outcomes, so they look like this, then they are mutually exclusive, which means that they cannot occur at the same time. Now, why this is important is because we use this definition or this term in our definition for the addition rule and then the special addition rule. Okay, so if event A and B are mutually exclusive, then the probability of A or B is just equal to the probability of A plus the probability of B. The general addition rule, so for just any two events, the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay, so you can actually use this rule for any case, but it just so happens that if your events are disjoint, okay, or they're mutually exclusive, then this part here is going to equal to 0, right? Because there's not going to be any intersection. You know, when you get these Venn diagrams here, which this won't look too good, but if you do this, there's not going to be any intersection there, right? Because they're going to look like this. There's going to be two separate circles. So there's not any intersection, so that would equal to 0. And so this part just goes away when you're talking about mutually exclusive events, right? But if they're not mutually exclusive, then you are going to have some intersection there, right? And so you need to account for that in there. Okay, so suppose that the probability of E, um, it's equal to that, probability of F is equal to that, answer the following questions, you just plug it in. Okay, so these are usually going to be given to you in your homework problems. You just need to know what the equations are that you need to use. For this one, we had to set up the sample space first to calculate these probabilities. So you notice that, like in this last one, they said, here's the probability of E and F, you know, calculate this. This one, they didn't give us the probabilities. We had to calculate them. And we were able to calculate them because we could use classical probability because we're talking about rolling a die. So this is one you would need to calculate the probabilities first, plug them in, and then calculate the probability of A or B. The complement rule is a very important rule. It looks pretty simple. It's just a little rule there, but it's actually one we will be using the rest of the semester because, like I said, we're going to be working with probabilities in some way the rest of the semester. The complement rule is just talking about the opposite, okay? If E represents any event and C, which is the complement, represents the complement of E, then the probability of the complement is equal to 1 minus the probability of E. Okay, so this is what the complement rule looks like kind of in a graphical form. You've got your sample space here, you've got your event E, and then everything else there is not E. So you can subtract from 1 because we know in our probability models, all those, the sample space, all the events have to add to 1, right? So if the probability of E is here, if we subtract it from 1, that's going to be everything that's not in E, right? So that's how we get that. So if we're doing a real application here, what is the probability that if you choose one card from a deck of spades, you will choose the ace of spades? Well, there's one card that is the ace of spades, right? There's 52 total cards, so we'd have 1 out of 52. What is the probability you will choose one card and you will not choose the ace of spades? Well, that's the complement, right? You either choose it or you don't. If you don't choose it, it's going to be 1 minus 1 over 52, which is going to be 51 over 52. So there's 51 options that are not the ace of spades, one option that is. And we'll use the complement a lot going forward, and just in different ways. Here you'll see we use the complement rule here to find what the probability of male is, because we had the probability of female. So since it's the complement of that, we could get to that outcome. And here's some other things that we were able to calculate based on this example. Again, here we're using empirical probabilities based on this data here and doing that. This is one of your homework problems, I think, or at least it was from my lecture class. They had some homework problems like this. I think that's why we were working on that one. 5.3 talks about independence and the multiplication rule. Okay, so we just talked about the addition rule. Now we're talking about the multiplication rule. So we have to talk about things being independent. Two events E and F are independent if the occurrence of event E does not affect the occurrence of event F. If they do affect each other, then they're dependent. Okay, so here are some examples of independent and dependent. The reason why we want to know about independence is if E and F are independent events, then the probability of E and F is just equal to the probability of E times the probability of F. All right, so if you can show that that's true, we can just multiply those probabilities together. All right, 5.5, we talk about counting techniques. All right, so counting techniques really just save us time. Okay, so let's say here a local restaurant provides the following choices: an appetizer, you can get super salad; the entree, you've got 4 different options; and the dessert, you have 2 options. How many different meals can be ordered? Well, let's look at the next slide here. This is what we would need to do to figure this out, right? We would write out, okay, for the appetizer, they could choose this or this. Then for the entree, they have 4 options, 2 options for the dessert. So someone could choose soup, then chicken, then ice cream. This is soup, chicken, ice cream, or soup, chicken, cheesecake, soup, chicken, cheesecake. Okay, so each of these are all the possible options people could choose. Well, who wants to write all this out every time? Nobody, right? Nobody wants to do that. So how can we figure this out without having to write out every single option? The way we can do that is using the multiplication rule of counting. Since these are all independent events, right? We can do this multiplication like we talked about in 5 back here. Was this 5.4? 5.3. I think we skipped 5.4. 5.4 I think is conditional probabilities, and so we don't do anything on that. So if you notice any homework problems that talk about conditional probabilities, let me know, because those aren't supposed to be included. That's just, we just don't have enough time to get to anything, especially in this short summer session, but we just don't have enough time to get to all of it. So we don't do conditional probability. But back to this, all we need to do is multiply all those options for each part. So appetizers, we had 2 options, entree 4, dessert 2. So 2 times 4 times 2 is 16. And you'll notice if we go here and count all these, we have 16 there. So it works the same whether you know, use the counting technique or if you actually go in there and do that. So these are some different options you can do there for counting techniques. Another thing in counting techniques is combinations, and we're going to use this in chapter 6 using combinations. So combination is a collection without regard to order. Okay, what we're going to do here is, let's say I'm going to put a class into pairs to work on a sampling project. There are 30 students in the class. How many different pairs can we create? Okay, so a pair means 2 people, right? So I'm saying how many different ways can I put 2 people together? Okay, so I could put like person A with person B, or I could put person B with person C, or person A with C, or B with D. I can do a lot of different ways, right? So the easy way to figure this out is by using combinations. The combination formula is actually here. So the way we write this or say this is from N, we're going to choose R items, okay? So N is our total sample size. R is how many items we're going to choose at a time, okay? So like we're going to make groups of 2. That means I'm going to choose 2 people at a time, okay? So we can use this formula in our calculator. So in our calculator, you need to know where that, let me turn this on. Go to math. I'm sorry, I didn't say where I was going. Go to math and over here to PRB, and we can go down here to the exclamation mark, and that is the factorial button. So we can use that when we're doing this, or since we're already here, you might notice right above here it says NCR, right? So we can actually do that to do our combinations. So the way we would figure that out is we put in our first number in there. So we're going to put in 30. Then I'm going to go back to math. PRB, go to NCR, and then choose 2. So it says from 30, I'm going to choose 2 at a time. How many ways can I do that? And I get 435. So there's 435 different pairs that I could make in my group of 30 people. Okay, what if I decided to create groups of 5 instead? So I could do a quick method on your calculator. If you want to just bring this up again, just go to second, enter, and it comes right back up. And so I can change this to 5 now. Okay, and then I get 142,506. So obviously a lot of different options for groups of 5 in my class. So the NCR button is in math. PRB, that's also where the factorial is. So if I wanted to do it the other way, I'll get the same answer. So here I'm going to do n factorial. So my n here is 30. It's just this takes a little longer to put in, I think, but you can do it either way. And then divided by r factorial is going to be 2 factorial. And then n minus r. So n minus r would be 28, right? 30 minus 2. And there we go. We get 435 there. I just wanted to make you aware of that formula because when you go to the help me solve this, you may see them bring up that formula and you might say, where is this coming from? But that's all it is. You don't have to use this formula. I would just use the NCR, but either way, you're going to get the same answer. So that's good to know that you can do it either way. All right, so that is the end of chapter 5. That's all about probability, and really it's setting you up for the rest of the chapters we're going to be covering, specifically chapter 6, where we start covering binomial probabilities. Thanks.